Hello, everyone, and thank you to Philip for the introduction and the opportunity to give this talk. What I'm going to talk about today is a joint work with Amitay Kamber. And let me explain what this talk is about. So I consider the special linear groups, which is SL and R. R is a ring. In this talk, it's going to be the integers, the rationals, or the real numbers, or Z mod QZ. And I'm looking at n by n matrices with determinant 1. And this forms a group. And if I take a positive integer, then I have a matrix in SL and Z, then I can reduce all the entries modulo Q, and this way I get a homomorphism from SL and Z to SL and Z mod QZ. And that is an important theorem in the theory of arithmetic groups called the strong approximation theorem. And the very special case of it is that this homomorphism that you see above is surjective. So this means that if you prescribe the entries of the matrix modulo Q, then you can find a lift in SL and Z, which will project to it. And what this talk is about is understanding this homomorphism and this surjectivity in a quantitative way. So I'm going to ask the following question. I specify the entries of the matrix modulo Q, and I want to find a matrix with integer entries, which also has determinant 1. And which projects to X modulo Q. And the theorem says that there is a solution to this problem. You can always find such an integer matrix. But the question is how big the entries need to be to solve this problem. And so this is in terms of Q. And I want to state two results. The first one gives an upper bound, and it says that if no matter how you specify the matrix X modulo Q, you can always find gamma with integer entries that projects to X, and the size of the entries is not bigger than Q squared times log Q. With some implicit constant that depends on the rank. Now for n equals 2, this is due to Sarnak with a slightly weaker bound, by which I mean that you have some power of the logarithm here, but this is not very important. And here is a corresponding lower bound, which shows that in general, you can't do much better than what the previous upper bound says. So this result says that for all modulus Q, you can prescribe the matrix modulo Q in such a way that for any lift, the size of the integers that you need to solve this lifting problem is going to be of size some constant depending on n and epsilon, times Q to the 2 minus epsilon. So what this means is that this exponent 2 is the best possible you can get. Now, again, for n equals 2 and for some special choices of the modulus Q, this is due to Sarnak. He wrote this down for Q being a power of 2, but it is very easy to do the same, just assuming that 8 divides Q. And perhaps you might even relax this to all even moduli. But it seems like that this approach will not work if Q is a prime. Okay, so what I'm going to do in this talk is that I'm going to explain the proofs of these two results. And then after that, I will talk a little bit more about the context. So in particular, this question can be asked in any situation where the strong approximation theorem applies. And there are a couple of other nice examples when where this has come up, and I will mention some of these later. But now I want to talk about the proofs, and first I'm going to explain the upper bound. And as I said, this is largely due to Sarnak, with a little tweak in the n equals 2 case, and it can be generalized to larger n, but I'm not going to talk about that. Okay, so how do you do this? We are actually going to give an algorithm. So not only I show that there is a lift with entries bounded by q squared times log q, but I actually also show it to you how you can find this lift. This algorithm has several steps, and the first one is that you try to find gamma 1, 1 and gamma 1, 2, so the entries in the first row, which project to x11 and x12. So the first step is that you lift the first row of the matrix. And what I want to achieve is that I want my matrix gamma to have determinant 1. And I certainly need to make sure that the entries in my first row will be coprime. Otherwise, I have no chance to make the determinant 1. And this is the only constraint that I have. This is something that I can solve with entries of the size q times log q. And what this means is that you take an arithmetic progression which with the prescribed residue modulo q, and the length of the arithmetic progression will be log q. And if you just randomly choose an element from these arithmetic progressions, then with high probability, you get two elements which are relatively prime. So this is an easy calculation to do. And this will give you the first row of your lift. Now you want to find the second row, and this is going to be done in two steps. In the first step, you just try to complete your matrix to any matrix with integer integer entries, which has a determinant 1. And in this step, you don't pay attention to what the residues are modulo q. You are happy with arbitrary integers, and this can be solved using the Euclidean algorithm. So you just want to write 1 as a linear combination of gamma 1, 1 and gamma 1, 2, and you can do this with the Euclidean algorithm. And you will find the solution with integers gamma 2, 1 and gamma 2, 2 tilde, which is of the same size as the entries in the first row, so q times log q. Okay, so now we have a matrix with determinant 1 and integer entries, and the first row has the correct residues modulo q, but we don't know anything about the residues modulo q for the second row, and the last step in the algorithm is to correct this. Now we want to preserve the property that the determinant is 1, so what we are going to do is that we are going to add a scalar multiple of the first row to the second row, and we are going to do this in such a way that gamma 2, 1 will have the correct residue modulo q. So to do that, I need to find a suitable integer such that when I add a times gamma 1, 1 to gamma 2, 1 tilde, I get something that has the correct residue modulo q. Now this can be solved, and if there is a solution, then it can't be bigger than q. And so we find a suitable A with this property, and then I'm going to add A times the first row to the second row, and then I get a matrix which will still have determinant 1. And now I have 3 entries, the first row and the lower left corner, which has the correct residues modulo q. But the determinant is also correct, and this means that the last entry also has to have the correct residue modulo Q. Okay, so this solves the problem. And what is the size of the entries? So gamma 1 is of size Q times log Q. And I'm multiplying that with something which has potential size Q. So the entries in the second row will be of size Q squared times log Q. And the entries in the first row are going to remain of size Q times log Q. And so from this you can see that it is kind of a strange situation, because the output of this algorithm will be asymmetric in the sense that the elements in the second row are much bigger than the first row. And if you look at this, then maybe the second theorem, where I say that you can't improve on the exponent 2, may look a little bit surprising, because you can find a solution where the first row is bounded by just Q. And essentially what the second theorem says is that you can't improve on the Q square exponent even if you allow the first row to be bigger. Yeah, so I just made this remark that the first row is much smaller than the second one. Okay, so this was just the upper bound, at least in the n equals 2 case. And now let me talk about the other direction. And first, let's make some elementary observations. So one thing that's easy to say is that you can count how many elements you have in SLN Z mod QZ. So in how many possible ways you can prescribe the residues modulo Q. And then you can also count how many integer matrices you have of determinant 1 if you bound the size of the coefficient. And if you play these two things against each other, this is going to give a lower bound on how big the entries needs to be. And you can do this calculation. So SLN 2Z mod QZ has roughly Q cube elements. And this is just because you have 4 entries and they need to satisfy one equation modulo Q. So that's the Q cube. And you can also determine how many integer matrices you have with determinant 1 with the coefficients bounded by some parameter t. And the answer to that is that this is roughly t squared. Now, in fact, here we know something much more precise. There is an asymptotic, so which says that this is asymptotic to a certain constant time t squared. This is a result due to Duke, Rudnick, and Sarnak. But for my purposes, this much weaker property is enough. And this is something that you can convince yourself easily that this is true. So what you can basically do is that when you select this matrix and you select the first row, then you can essentially choose anything you like. The only thing that you need to pay attention to is that you want the elements to be coprime in the first row. But this will hold for a positive proportion of your choices. And on the other hand, once you chose the first row, the second row is almost uniquely determined. And the reason for that is that any two choices for the second row differ from each other by an integer multiple of the first row. And it means that if you take a large integer multiple of the first row, then the second row will become much bigger. So the reason why this t-square is coming from is that this is how many choices you have for the first row, and then you don't have too many choices for the second one. Okay, so if you compare these two counts, then what you can conclude is that there is some x in SLN to Z mod QZ, such that if you want to lift this to SL2Z, then you need entries of size at least q to the 3 over 2. And in fact, this is also true for 99% of the elements in SL2Z mod QZ. Okay, now in the other direction, there is a result by Assing and Blomer and Yama and Kamber, which says the following, that for 99% of the elements in SLNZ mod QZ, the best lift in SLNZ will be of size q to the 1 plus 1 over n. And this, if you take n equals 2, that's 3 halves. So what this says is that this lower bound that you get from counting is optimal if you are not looking at the lifting problem for the worst case, but you are looking at only a typical 99% of elements in SLNZ mod QZ. Yes? Is there a question? I just heard something. Okay. Now, if you think a bit about this, then if you take an arbitrary element x of SLNZ mod QZ, then you can write it as a product of y1 times y2, such that y1 and y2 is in the good 99% of SLNZ mod QZ. So they are elements which are easier to lift, namely that you can find a lift with entries of size q to the 1 plus 1 over n. Now, if you do that, then you get a lift lift of x, which will have size q to the 2 plus 2 over n. And what we proved with Amitay is that you can't do much better than this if you take the worst x. So for the worst x, the best exponent you get is q squared. Yeah, so here is that result again, that there is always a choice of x in SLN Z mod QZ, such that there is no lift with entries smaller than q to the 2 minus epsilon. So what this shows is that if n is large, then the worst case is much worse than the average case. And basically as difficult to solve the lifting problem as it possibly can be. Okay, so I want to tell you a bit about the proof of this result of how to find an element which is difficult to lift. And here is a piece of notation. Given an element in Z mod QZ, we denote by absolute value of alpha the smallest absolute value in this residue class alpha plus q times z. So the first step in the proof of the theorem is the following lemma. So I consider two elements of Z mod Q square, alpha and beta, such that alpha is the square of beta, and beta is relatively prime to Q. And then I consider the diagonal matrix of beta inverse and beta. So, and I want a lift of this modulo Q. Now, alpha and beta are living in Z mod Q square, but I'm making this congruence assumption only modulo Q. And what I claim is that in this case, I have this equation that alpha times the first diagonal entry of the lift plus the second diagonal entry is going to be congruent to 2 times beta modulo Q square. I will explain in a minute why this is true, but first I want to explain why this is good for us. So I'm going to use this lemma with suitable alpha and beta such that 2 times beta is going to be large. So the smallest integer in the residue class is going to be almost as big as Q square. But on the other hand, alpha is going to be something very small. And if that's the case, this will imply that gamma must have a large entry. Why? Well, assume that both gamma 1, 1 and gamma 2, 2 would be smaller than this number that I claim here. And then if I look at alpha times this bound plus 1 times this bound, then I would get something which is smaller than 2 times beta. But that's not possible because it is congruent to 2 times beta modulo Q square. Now, what is very important here is that this congruence is modulo Q square and not just Q, and this is what allows me to show that to get a bound, to get a lower bound on gamma, which is of the order of magnitude of Q square. Okay, so how can I get this congruence modulo Q square? So I want to make first the observation that this congruence is true modulo Q. And that's just trivially the case because gamma 1, 1 is congruent to beta inverse modulo Q, and gamma 2, 2 is congruent to beta modulo Q, and alpha is equal to beta square. So this means that this entry, alpha times gamma 1, 1, is going to be congruent to beta modulo Q. So this whole thing is just congruent to 2 times beta modulo Q. But I claim here something more. I claim that I also have a congruence modulo Q square. Now, how can I get such a thing? Well, imagine that you have this 2 by 2 matrix and you know what it is modulo Q. And then you perturb it by adding to each entry something divisible by Q. And what you know is that the matrix that you have will have determinant 1 because that's the lift that you are looking for. And you write down this equation that the determinant is equal to 1. And then you have a congruence. You have an actual equation that the determinant is equal to 1. And if you just looking at this modulo Q square, then all the quadratic terms in the determinant are going to vanish. So you get a linear equation, modulo Q square, for your entries. And all that I'm claiming is that the linear equation that you get is going to be precisely this one that I wrote here. So this is a simple calculation to check that this is indeed the linear equation that you get. So this lemma is either trivial or false. And I hope you will trust me that it's true. But it's not very deep. The more interesting part of the proof is that you can find a suitable alpha and beta in Z mod QZ such that alpha is equal to beta square and alpha is small, but 2 times beta is bigger than q to the 1 minus epsilon. Now, I realize that this might be a little confusing, so the q in this theorem corresponds to q square in the lemma. Imagine that alpha and beta is in z mod q square z, and then you get here q to the 2 minus epsilon. But the upshot of this is that if you combine this theorem with the lemma, so you plug in the alpha and beta given by this theorem, and you try to lift this particular diagonal matrix, then you can't find a lift which would be smaller than q to the 2 minus epsilon. So my next goal is to talk about the proof of this theorem. Now, for simplicity, I will explain the proof of this theorem in the case when q is a prime. And now you might feel that I'm cheating because I said that the q in the theorem corresponds to q square in the lemma. But this is not very important. In fact, what the proof that I'm going to explain is equally valid unless q has a lot of small prime divisors. And in that case, you need to give another proof that I don't want to talk about. But the proof that I'm going to explain is actually relevant to perhaps the most interesting case of this theorem. It will just be easier to think about the case when q is a prime. Okay, so let's get going. So the first thing that I'm going to use is the Legendre symbol, which is alpha over q, and it is defined as 1 when alpha is a square modulo q, and it is minus 1 when it's not a square. And a classical fact is that this is multiplicative. And so why this is interesting to me? Because this implies that if I look at 2, and 2 is not a square modulo q, and also 3 is not a square modulo q, so I have 2 over q times 3 over q, that's going to be equal to 6 over q, and if this is minus 1 and this is minus 1, then then alpha 1 times alpha 2 over q is going to be equal to 1. So what this tells me is that if 2 is not a square and 3 is not a square, then 6 will be a square. And in other words, this says that among these 3 numbers, at least one of them will have a square root in z mod qz. Now that's very good because that's a possible candidate for alpha. It's a small number that has a square root. And in fact, it is easy to show that if you take such an alpha, one of these guys, then for the corresponding square root beta, it will be true that 2 times beta will be bigger than square root of q. Simply because if it was smaller, then 2 times beta squared would be smaller than q square, but it would have to be equal to 4 times one of these numbers. And 4 times one of these numbers is not a square as an integer. So that you can have a congruence modulo q, you need to wrap around, and that will only happen if 2 times beta would be bigger than q to the 1/2. So this very simple observation already gives us some mileage, and we can prove this theorem with epsilon equals 1/2 just by this very simple observation. But if you just take one alpha, then you can't really hope to get any further than this. So I guess if you take Q to be of form n squared plus 2, 3, or 6, then the corresponding square root is going to be n, and that will be not much bigger than this q to the 1/2. Okay, so we need to do something more to improve on 1/2, because we want to get to 1 minus epsilon. And what we are going to do is that we are going to use many alphas. So I fix a number capital N, which is going to be chosen sufficiently large depending on epsilon. And I'm going to find some alphas, alpha 1 up to alpha n, and corresponding betas, beta 1 up to beta n, in Z mod QZ, such that alpha j is the square of beta j, and the alphas are bounded by some constant depending only on epsilon. Well, they really do depend on capital N, but the capital N depends only on epsilon. And I want these alphas to be squares on their own right. So what do I mean here? Now, you could imagine that maybe one choice for alpha would be 2. So say 2 is a square. And if 2 is a square, then also 8 is going to be a square. Just because if you multiply by 2, the square root of 2, that is going to be the square root of 8. But this is not unrelated to the fact that 2 is a square. So I want my alphas to be squares not for these trivial reasons. And the way to formalize this condition is that if you take the ratio of the alphas, then they are not squares of small rational numbers. So if I have 2, then I don't want to have 8. Okay, so I find a list of these residues alphas which have square roots. And then I'm going to form this set A, capital A, which will be all the products that you can form from the betas. The exponents k's, k1 up to kn are chosen from arbitrarily from 0 and 1. So this expression that you see here, this is all the different products that you can make with the betas. Now, what I hope for is that if I take my capital N to be suitably large, then there will be a good choice of beta for which 2 times beta is very large. If I manage to do that, then I am in business, because for all these choices of beta, beta square is not going to be very big. Because if you have a product of betas, then the square is going to be the corresponding product of the alphas, and each of the alpha is bounded by C epsilon, so beta square is not going to be bigger than C epsilon to the n. Okay, so I will suppose to the contrary that I'm not so lucky and I can't find a suitable beta where 2 times beta would be big enough. So I make the assumption that for all of these choices of beta, 2 times beta is going to be smaller than q to the 1 minus epsilon. Okay, and then I will use a little bit of additive combinatorics. And I consider what is called a Bohr set, which is just defined as the set of residues x, which has the property that x times beta is smaller than q to the 1 minus epsilon for every choice of the beta in the set A. And what my indirect assumption says is that this set is not trivial. It's not 0 is not the only element in this set, because 2 is also contained in it. So my assumption was that 2 times beta is less than q to the 1 minus epsilon for all choices of the beta. Okay, so before I go any further, let me just say something about Bohr sets, how to think about these. So I call the set A as the set of frequencies, and I call this number here, this q to the 1 minus epsilon, as the radius. So the way to think about this is that the set A lives in on the Fourier space, and the x's live in physical space. So what you should think about is that to A there are some corresponding characters, and the Bohr set is the set of points in physical space where all the characters are very close to 1. Okay, so this is how to think about the Bohr set. And an important result in additive combinatorics is that Bohr sets can be closely approximated by generalized arithmetic progressions. So here is the result. Given the Bohr set, I can find elements u1 up to ur and integers corresponding to them, L1 up to LR, such that if I form the generalized arithmetic progression, which consists of all the linear combination of my U1 up to UR, I think about these as basis vectors. And I can let the coefficients go NJ goes from minus LJ to LJ. So think about this as you have this box. And what will happen is that this box covers the Bohr set. On the other hand, if you increase the radius of the Bohr set a little bit by some constant factor, then this is going to cover the generalized arithmetic progression. So this is a standard result in additive combinatorics. But what is not so standard is that usually this is applied with a radius which is much bigger than what I have here. It's more typical to apply this with small constant times q. But there is a nice feature when you apply it with a small radius like this, so that I'm having q to the minus epsilon saving over the maximal size q. And namely, this feature is that I can have this approximation with R, so the rank of the generalized arithmetic progression, and the constant that appears here, which is such that it depends only on epsilon. And it doesn't depend on how many frequencies I add. So in a typical application of this result, you would have that the rank of the generalized arithmetic progression would you could bound it by the number of frequencies that you throw in. And that would be very bad for us because you can see that this set of frequencies is going to be huge if I take capital N to be large, and I'm going to take capital N to be very large. And I need to keep the rank and all the constants that are arising controlled. So this is an important feature for me. Okay, so how to use this to complete the proof? Now let's observe the following. I'm going to look at the transformation which moves x to beta j times x. And so this has some action on physical space, and then there is a dual action on Fourier space, which is also multiplication by beta j. And if you look at my set of frequencies, which is all the products of the betas that you can get, then you can observe that this set of frequencies is almost invariant under multiplication by beta j. if I have here a frequency which doesn't involve beta j, and I multiply it with beta j, then I get something which is in my frequency set. And if I have something here which involves beta j, then when I multiply it by beta j, then I get beta j square, which is alpha j, and alpha j is small. So anything that I can get when I multiply my frequency set with beta j is either already in my frequency set, or it is just a small multiple of something which is already in my frequency set. So what this means is that when I apply this transformation, x going from beta j to x, this is not going to change my Bohr set too much. If I apply this transformation and I adjust the radius of the Bohr set a little bit, then the image is going to be contained in that adjusted Bohr set. And so what I can do with this is that I can think about this transformation as some action on my generalized arithmetic progression. And it will turn out that this is going to be a linear action. So I can define some sort of matrix for this action with respect to the basis u1 up to ur. So there will be a corresponding matrix with integer entries of rank r that corresponds to this transformation. And then I can prove some properties of these matrices that I get. And one property is that the matrices that I get for the different j's are going to commute. The other property is going to be is that if I apply the transformation 2 times, then that will correspond to multiplication by alpha j. And because alpha j is a small number, its matrix is just going to be alpha j times the identity matrix. Okay, so at this stage, I can forget everything. And I just think about r times r integer matrices, which are commuting with each other, and their square is a scalar matrix. And then I can ask myself the question, is this possible to have such matrices? And it turns out that if you make a capital N, so the number of matrices that you have sufficiently large in terms of the rank, then there must be 2 of them which are scalar multiples of each other for some rational number. And this will imply that my original alphas were not independent of each other, which contradicts to how I chose the alphas, and this is the end of the proof. So again, I just want to highlight that it is very important for me that I can choose capital N to be suitably large in terms of R, and this is going to make my frequency set really huge. And it is very important that in this structural result for the Bohr set, I can control the rank in terms of epsilon and independently on the number of frequencies that I have. Okay, so this finishes the part of my talk about the proofs. And now let me just briefly mention a few analogous problems which arise as trying to quantify various other cases of strong approximation, which are interesting problems. So the first one is concerned with the Ramanujan graphs. There is a spelling error here, which were constructed by Lobotsky, Phillips, and Sarnak. And so these graphs are given by, you need to choose 2 primes, P and Q. P is a small prime, Q is a large prime, and P is a square modulo Q. And a condition that I didn't state here is that P has to be congruent to 1 modulo 4. And then they define a certain graph, and you can ask the question is, what is the diameter of this graph? And this is going to be equivalent to the following lifting problem. Namely that you consider the Hamilton quaternions with entries in the ring Z adjoint 1 over P. And you look at quaternions with unit norm, and there is a congruence condition modulo 2. And then you look at the projection modulo Q. And now you can ask the question that if you prescribe the reduction modulo Q, what is the smallest element in gamma which projects to X? And how small can this be periodically? So now you have a projection prescribed modulo Q, and but you are not looking at the size of the coefficients in the ordinary absolute value, but instead you are looking at it periodically. And so this question is it corresponds to the problem of determining the diameter of the Lubotsky-Phillips-Sarnak-Ramanujan graphs. And what the Ramanujan property implies, that was originally proved by Lubotsky-Phillips and Sarnak, is that if you look at the almost diameter, that is, you want to know what is the best lift of 99% of the elements, then this is going to match the lower bound that comes from the analogous counting argument. Sardari showed that if you look at not the almost diameter, but the diameter, then this is going to be at least 4/3 times the almost diameter. Now, this 4/3 is the same 4/3 that appears between the ratio of the worst case lifting for the problem that I was talking about and the 99% average case. So perhaps it's not unreasonable to expect that this 4/3 would be the truth, but this is the matching upper bound is still open. In fact, I'm not completely sure what is the state of the art on this because I recently was made aware that there is some literature on this in the cryptography community. But it might be the case that the best rigorous upper bound is coming from twice the average case that you can get with the same argument that I explained in the problem of lifting SLN Z not QZ. Then here is another setting which is interesting. Which corresponds to the so-called golden gates that were introduced by Sarnak, which is interesting in quantum computation. So you can look at the same group gamma that I told about before. So this is the unit quaternions with coefficients in the ring Z adjoint 1 over P. And satisfying this congruence condition modulo 2. But now, instead of projecting modulo Q, you embed it into the real points of the unit quaternions, so which is isomorphic to SU2. And then you can ask the question that if somebody gives you an element of SU2 and some epsilon, then what is the smallest gamma periodically, such that the distance between gamma and X is smaller than epsilon. So now in this setting, you look at the Archimedean distance in the approximation instead of a prescribed reduction modulo Q. And you want to minimize periodic absolute value for the lift. But this is a completely analogous problem. And then, so here is just some example of these golden gates. This is what you get when you take P equals 5 in the Lubotsky-Phillips-Sarnak construction. You get this 6 So these are three unitary matrices, but you also need to take their inverses, and then there will be six. And so you can ask the question that what happens if you want to approximate an element in SU2 with a product of these guys, and if you allow an error of epsilon, then how many of these matrices you need to multiply together to get a good approximation. And again, the state of the art is quite similar as before. You can talk about the almost diameter, which means that what is the best solution that you can get for 99% of the elements in SU2. And again, it is known that you can achieve for 99% of the elements the same rate as the lower bound that comes from counting. This was also proved by Lubotsky, Phillips, and Sarnax, and using spectral methods. And the diameter is again probably expected to be 4/3, the same 4/3 times the almost diameter. And here there is also there is a lower bound due to Sarnak, so you can find an element in SU2 which is very difficult to approximate, and you need the 4/3 times the almost diameter to do this. There are some bounds in the other direction, but they don't match this 4/3 yet. And then maybe let me just very briefly mention a fourth setting where you specify a matrix in SLN R, and you specify an integer q, and you want to find an integer matrix n by n, which has determinant q, such that when you normalize the matrix by dividing it by q to the 1 over n, to get a matrix with determinant 1, then it will approximate the prescribed x with good precision. And then you can ask what is the best error that you can get. Sardari proved that there is some x that you can't do better than q to the 1/4. And on the other hand, you can always do it with q to the 1/3. And I have a joint work in progress with Amitay where we show that you can yes, so this k is supposed to be n. Apologies for the mistake. So you can prescribe x in the n by n case, such that you can't do better than q to the 1 over 2n. And there is for if you choose q, not arbitrary, but for certain q's, you get a matching upper bound, and these good q's have positive density, and in particular, it applies in the case when q is at the power of a fixed prime, which is perhaps the one of the most interesting cases. So in this analog of the problem, the optimal exponent is this q to the 1 over 2n. Yes, and I want to finish here. So thank you for the attention, and ask me questions.